it seems that nature is singing a siren song for us, encouraging us to believe in all this crazy stuff. Is she teaching or teasing? Well, here I am. I've jumped ship, gone into this cold water. There's the siren, nature, and I've left the safety of known reality on the ship and gone into this. And, well, is she teaching or teasing? We'll find out. You can see the mixture of hope and fear, and the mixture of kind of disdain or indifference on, but well, or maybe sympathy. I don't know. You could read, what do you read into that face? I'm not sure. And that's what the point. We're not sure. Fortunately, we can check. We'll find out, because these particles, these super partners, these hypothetical things that we seem to need in their virtual form should also exist in a real form that you can bring out if you supply enough energy to bring them to the surface. And we can estimate what those energies are, and they're not so high that they will escape the LHC. So there's going to be a trial by fire of this picture of unification, this grand picture of bringing the forces together and bringing the different kinds of matter together. Either Susie's supersymmetries, we call it fondly Susie. Susie's new particles will show up at the LHC and we'll be happy, or in the trial by fire, these ideas will go up in smoke. So they may go up in smoke, but another thing that can happen is that when the grid analyzes the events to see what they mean, they'll find, of course, usually 999,999,999 times out of a billion, that what's happening is fully accounted for by our core theory, but 1 in a billion times, or whatever I said, there'll be something different. Something that we can reconstruct, that there was a particle that decayed into the known particles, but that wasn't one of the ones we saw before, that can be fit with the properties of a superpartner. And so the superpartner will be saying, here I am, and there's another one, here I am, and then the golden age will have commenced. So, that's where we are. And I hope I've conveyed to you a sense of why this is an especially exciting time to be a physicist, but not just an exciting time to be a physicist. It's all of our world that we're learning is a richer place than we thought it was. Not everyone can invent the equations, but everyone can relate to the concepts, I hope. The idea that the world is a richer place than you thought it might be, that empty space is not really empty, that it's dynamic, that the fundamental laws are actually beautiful and symmetric and human beings can figure them out. I think those are very exciting things for any thinking being, and so it's an exciting time to be a thinking being. So, thank you for your attention. Any questions?
Thank you very much, Professor Wilczek. I think we'll have time for just a couple of questions.
Okay.
Let me point out first, if I may, that Professor Wilczek has suggested questions.
Yeah, I find there's often an awkward pause at this point when no one can work up the courage to ask a question. And so I have some suggested questions. You don't have to use these.
Well,
just hold on.
we'll get you.
Don't spoil my jokes. So here are some suggested questions. What about dark matter and dark energy? Will the LHC destroy the world? What's it like to win a Nobel Prize? Well, you can ask any question you like, though. Okay, so.
You are interested in enriching our overall knowledge of the world.
Yes.
I'd like to ask you a question a little bit different from just your emphasis on the physical world. And anything that you might want to say about consciousness. For example, does consciousness can it be reduced to physical matter? Do you see any kind of consciousness within the matter which you have systematized? Or any ideas at all? I'd just be very curious personally about
Right.
this whole idea of maybe how human consciousness is somehow different or not, or any ideas you have.
Right.
May I repeat this for the people in the
yeah.
overflow? The question, to reduce it to a very short one, is can you say anything about consciousness from your studies of the physical world?
Yes. So the most definite thing we can say is that we do these extremely precise experiments, both at accelerators and in many other kinds of physics laboratories. And so far, it's never been necessary to adjust our description of the results of these experiments for what people in the neighborhood are thinking about. The equations don't seem to care what anybody's thinking about, don't seem to care what anybody's consciousness is doing. So if we believe that causality could work both ways, it's very hard to see how these kinds of basic interactions are responsible for causality. They seem to, for consciousness, they seem to be quite different things. My own feeling is, my own very strong intuition is that we don't need new laws, new fundamental laws for how tiny things interact to account for consciousness. We don't need fundamental laws beyond these laws of how the small things interact and building up to more complicated things to describe anything in the physical world. But that we need new concepts. We need new ways of working out unobvious consequences of the laws we already have when applied to large objects where different kinds of regularities emerge. So I think physics gives us a very firm foundation for investigating questions like the nature of consciousness that tells us that where not to look, really. And you shouldn't be looking to mystical properties of matter. You should be looking to understand better the consequences of the laws we already know.
We have one over here.
Right.
So how do you take these collisions and then use them to model the infinitesimal events that occur in that?
The question was, how do you take these collisions and use them to model the infinitesimal interactions in matter?
Yeah. It's complicated, but the basic underlying idea is that our description of the physical world is based on something called quantum field theory, which says that for every kind of particle, every kind of fundamental particle, there's a medium, an ether-like medium that fills all space. It's quantum field that has this kind of spontaneous activity I showed you, that is sort of the primary reality the particles we see are kind of the epiphenomena, the little disturbances in this where some of those fluctuations make it so they can persist for a long time. That's what we call a particle. Now, when we study the fundamental interactions at a place like LHC, we're learning how the different fields interact with each other, how they affect each other, because we're seeing when you have particles which are excitations in one field and another field, how they can interact to produce excitations of yet a third field. So we go from the particles to reconstruct the properties of the fields and then solve the equations of the fields to see how things are actually behaving in space and time. So that's the kind of process. Well, so far it's been very successful and very internally consistent. For instance, those pictures I showed you of the fluctuations of gluon fields in empty space emerged as a kind of byproduct of computer calculations that were designed to figure out why protons weigh what they do. So solve the equations that we have for quarks and gluons to try to determine what the theory predicts for the mass of protons. Couldn't be more down to earth and more testable. It's what you and I weigh, right? So if you aren't satisfied with your weight, you need to go on a diet. So you can blame these calculations for calculating that the protons have too large a mass, for instance. Anyway, now it's late. Right, what was it? Okay, so, but in the course of doing those calculations, which can be checked, because we know the mass of the proton experimentally, so we can check that the calculations are actually reproducing nature. And not only the proton, but the neutron, pi mesons, rho mesons, all those have to be successfully reproduced, and they are. So we have great faith that what the computer is doing corresponds to what nature is doing. And that's why we can have faith that these pictures are a faithful and accurate representation of the underlying reality. So we can't, of course, see these things directly. We have to do a lot of fancy image processing, but because there are many things we can check coming out of the same framework, it gives us faith in the parts that we can't check directly.
Thank you very much. I think we're going to have to stop the questions at this point, but I will point out that Professor Wilczek is an accomplished author and in fact has written several books, and he has a new book out, The Lightness of Being. And copies of the book are available in the lobby, and Professor Wilczek will be there signing copies. And
yeah,
you might
and
have
I'll
some
answer
ideas.
Your questions too.
Yeah.
For this.
You even have some ideas available. I think we should thank Professor Wilczek once again.